So after looking at all these hyperbolic surfaces, it opened more questions in our minds as to if these are all hyperbolic surfaces, this isn't quite like the sphere where there's only this one surface and we can kind of do things on the surface that make sense in a sort of a constant way. But these all look different. So how do we do geometry that is meaningful in a general sense on all of these different surfaces? So we wanted to look into that a little further. So these kind of questions came up. Can we do straight edge and compass constructions on these weird surfaces? Or can you prove that two polygons are congruent like we do in Euclidean geometry? These are the kind of questions that popped into our mind. So the short answer is yes, you can. You can by using a flat model of a hyperbolic surface. So if you've got a surface that looks like this trumpet here, or a surface that looks like a crocheted model, one of those kind of surface that we've looked at already, we want what I'm going to call is a generic surface to do our constructions on, and that generic surface that I'm going to talk about is the Poincaré disk model, which is used to do analytics on in hyperbolic geometry. So let's take a look at the Poincaré model and how that is that generic surface that we're searching for. So if you look at the blue structure here, this is the upper piece of a hyperboloid of two sheets. So this would be your axis of revolution. And this right here is the Poincaré disk, which is a disk of radius 1. We call that a unit disk, centered at 0, 0, 0. And the edge of it is considered to be infinity, just like the edge of this hyperboloid up here would be considered to be infinity, at infinity. Okay, so the projection is done from this point down here at 0, 0, negative 1. And what happens is, this right here, if we think about our bug walking along a straight path, he can go straight ahead, straight ahead, straight ahead, neither turning left nor right, and go off the other end here at infinity. That's considered a straight line path on a hyperbolic surface. Okay, so we want an equivalent structure down here on the Poincaré disk. So if I put my eyeball down here and I project each one of these points, if you can imagine that, down onto this surface here, each one of these points is mapped down onto that red line, and your structure, your equivalent structure to that brown curve on the outside of the hyperboloid ends up being this red circular arc. So this is the generic model that we're talking about being able to use. So I want to take another look at it in 3 dimensions using Octave. So here's a program I wrote in Octave that is going to allow me to rotate the hyperboloid in real time and try to get a better feel for what's going on with this construction of the Poincaré disk. So if I run this, I'm going to get this graphic here. Let's make it a little bigger, and I can rotate it into any view. Okay, so first I want to talk about this saddle over here so we can think about negative curvature points. So the point on top of this saddle in this view is concave upward. But if I rotate it into this view, it's concave downward. Okay, so that's negative curvature. And if you can imagine, every point on a hyperbolic surface is considered to have negative curvature. Alright, so now I'm going to draw your attention over to the hyperboloid and the circle, because that's my Poincaré disk. The hyperboloid is centered right over the Poincaré disk. Okay, so they have the same axis of revolution. Right? And so I can talk about any path that my bug could take. So you can see down in there, he can walk anywhere he wants to, up one end, down the other, up one end, down the other, along the side, like that, down the other, anywhere he wants to, as long as he doesn't turn left or right, he's walking in a straight path. So looking at a little deeper, let's try drawing one of those paths. So here's my bug. Let's say he decides to walk down there and up the other side. So he's made one of those paths. All right, so I want to project that path down onto the Poincare disk, what I'm calling a generic model of hyperbolic space, of a hyperbolic plane. So here's my eyeball down here. So if I look straight up here at this point, I want to map that down. It's on the edge down here. So each one of these points is going to be mapped down here, and if that happens, you're going to end up with the equivalent construction on the Poincare disk that has all the same properties. And that is your circular arc, your straight line that represents this so-called straight line path on the outside of this hyperbolic surface. So here we are. We popped over to non-Euclid, which is that so-called generic model of any hyperbolic surface. And so we can do constructions on this model. All we need is a way to make points and lines and circles. All right, so points like we do when we teach constructions in high school. So free point, so here's a point as we know it, a non-dimensional object, point, point, point. All right, and then we can make lines. There's a line. Oops, that's a little line. There's a line. All right, so there's a line. So you can make lines and you can make circles. All right, circles. And you'll notice that the center doesn't always look like it's in the center of the circle we drew, and I'll explain that in a minute. But those are the tools that we would need to be able to do straight line constructions in order to do any constructions on the hyperbolic surface. Now, let's clear that out a minute. Now, what makes this a hyperbolic surface, a non-Euclidean surface in the first place? Why is that the case? Remember, it's because the parallel postulate doesn't hold. So, like we do when we're teaching high school, we like to draw on something that students have already digested. So there is something we've already digested having to do with these the parallel postulate not holding, and that's on the surface of a sphere, another non-Euclidean surface. All right, so let's try that. So if I put a line on here, oops, we only need one line, and we put a point on here that's not on the line, I want to illustrate how the parallel postulate doesn't hold here. So I'm going to rotate this for a second. All right, let's put some lines through my point that's not on my original great circle. Remember, great circle is a line. All right, there's one. Oops, I don't want that one. Let's do another one through this point here. All right, let's do one more. Try to get it in there. All right, now let's rotate my original line here and check and see if any of those lines intersected it. Well, they all did. They all intersected. Okay, so if you can imagine, we're not able to draw any line, any great circle, that isn't going to intersect this original line. So that's why this is a non-Euclidean surface, because the parallel postulate doesn't hold. Okay, so why is the Poincare disk a non-Euclidean surface? All right, so let's check. So let's draw a line. There's a line. Oops. And let's draw a point. There's a point, not on the line. And let's see if we can draw some lines through that point that don't intersect that line. So line. All right, so here we go. There's one. Let's do another one. There's one. So I can do a bunch. And you can see where this is going. There's many ways I can draw lines through this point, infinitely many lines. And as long as I don't go over that, they're considered parallel. So here's my original line. Here's my point not on my original line. And I can draw as many lines as I want, infinitely many lines through this point that don't intersect this original line. And that illustrates that the parallel postulate doesn't hold on this surface, and that is why this is another non-Euclidean surface. So we ended up being able to answer our question in most ways, our questions of can we do basic constructions on the non-Euclidean hyperbolic surface. So we showed that we can do them on the Poincare disks, and these are the points I want to make here about that. So points exist on the open Poincare disk and have the meaning that we're used to points having. All right, the second point here. The shortest path between 2 points is a circular arc, which is orthogonal to the edge of the unit circle. So these are our lines on hyperbolic planes. And these circular arcs are analogous to lines on the Euclidean plane. So circular arcs are our line structures on hyperbolic surfaces. Okay, so there's this process called circle inversion, which allows us to do constructions on the Poincare disk. And so that's what's going on behind the scenes in programs like non-Euclid. So, we were wondering what is going on behind the scenes that this program is doing to be able to create these constructions that we're telling it to create. So it's this process called circle inversion. Okay, so circle inversion across an arc in hyperbolics is like reflecting over a straight line in Euclidean space, and it preserves distance. So down to here, circle inversion can be done by hand, like Escher did with a straight edge and a compass. And that is a totally another subject altogether beyond the scope of this. It does look like a lot of fun to learn. And maybe some of us would be interested in figuring that out in the future. And the last point here is that circle inversion can be done and is done using programs such as GeoGebra or non-Euclid, and that's what I said was going on behind the scenes, and that's what we were wondering about. What's going on? Why can we do all this stuff? It's because of circle inversion on this generic flat plane surface that allows us to do regular geometric constructions and proofs like we would do on a surface, a flat plane Euclidean surface that we're used to doing them on. So they can be done. They can be done, but the process is a little different. So we don't know much about circle inversion yet, if anything, but hopefully we've piqued a few people's curiosity, and you might want to look into that in the future and learn something new about how that's done. So thank you for listening, and I'm just going to show you our reference slide, and we'll take some questions.